Okay, so I will proceed with the third lecture. And let me first recall the important results we proved yesterday. And this was, first of all, about reductions. So we studied reductions associated to a topological splitting of the bundle. So we suppose that L splits in this way, with L is a line bundle, line subbundle. Of E, and we supposed that L is not isomorphic with its orthogonal complement, and then we studied the corresponding subspace of reductions associated with this topological splitting. So this is an important part of our moduli space, so of projectively ASD connections on E, inducing the fixed connections A on the determinant. And we showed that this is isomorphic to a torus. So, and this was either empty, and this happened precisely when C1 of L squared tensor D dual is not GS-ASD, or a B1 dimensional torus, B1 dimensional torus, when the opposite happens, when is GASD. So this was the result we showed. And also we introduced the notion of twisted reduction. I will come back immediately. But before doing this, suppose that we are in the, let's say, difficult situation. Unfortunately, this is the situation we'll have for class 7 surfaces, and the explanation is very easy. In that case, we have B plus is 0. We'll see today already. This means that all the classes are anti-self-dual. Maybe I should recall what this precisely means. We have here a de Rham cohomology class. Yeah, so this I mean here by the Chen class of this line bundle regarded as a de Rham cohomology class. And I say that this class is GASD if its harmonic representative has this property. Okay, so the point is, again, maybe I should point out this important splitting. We have an harmonic space here, H, which depends of G, of course, but is identified with the de Rham cohomology class group space, which is a topological invariant. This object here is independent of the metric. Yeah, so this object is independent of the metric. This one, as a set, of course, does depend of the metric. But it is as soon as you have G, is canonically identified to a G-independent topological invariant to this one. And here we have the composition like this. As soon as this vanish, as this vanishes, this subspace vanishes, and every class, every de Rham cohomology class will have a harmonic representative which is here, so we are in the difficult situation. Yeah? So it's very important in gauge theory to understand this splitting. And what is here interesting to see is that, of course, the dimensions of these subspaces, of these summands, are constant, are topological invariants of the oriented four-manifold M. However, their images in this space, which is G-independent, which is well-defined, depend of G. So you should think of a splitting of this vector space, which is G-independent, but the summands do depend on the metric. Yeah, this is very important to understand. Now, before proceeding, I would say something about very interesting result about the local structure of our moduli space around a torus of reductions. Because we did this carefully, I take this opportunity to explain also this briefly. These are results which I proved explicitly with all the details in the two papers I mentioned yesterday at the beginning of the lecture. And they are available only there, and I will explain why in the past these phenomena have not been studied. This is again because in the past the topologists were interested in the simply connected case. So, yeah, if B1 is 0, then our torus reduces to a point, of course. This is the point. Yeah. Now, if we fix a connection B in this space, I denoted it like that. So this was the set of all connections on the Hermitian line bundle L satisfying this property. So F B plus is so this was the equation which has been denoted in this way by star A. Okay, so I showed that in fact yesterday this was the idea behind this result, this identification we showed here. The idea was that in fact if this equation, if compatible, in fact determines precisely not only the plus component of the curvature but the curvature itself. Yeah, this was the idea. Anyway, so and then we have a corresponding reduction, AB, which is B. Here we take A tensor B dual. This is a corresponding split reduction. So here we have an abelian object, so in the space of the connections on L. And now we go in the moduli space we are interested in, which is a moduli space of connections on the two bundle E. So this is the corresponding split connection, you see? And okay, the condition that B satisfies this equation was in fact equivalent to the condition that AB is ASD. In this way, we obtained the equation star A. So this will be in the space of solutions of the projectively ASD equation. And now the point is that the elliptic complex associated with such a connection, split connection, is a direct sum canonically, splits. And splits in this way. So the elliptic complex is a direct sum. is a direct sum. It's a direct sum of two elliptic complexes. So first one is this one. This is the standard plus elliptic complex, or ASD elliptic complex, EA1M, EA top plus M0. You see, this part is independent of connections. This is just an elliptic complex associated with M. This, of course, is D plus here, and here you have D. And another one associated with this bundle. So let me, this is an important line bundle. Let me, we have used it yesterday. Let me denote it by S. And now, the point is that the connection induced by B and A on S is ASD. This is what this equation tells you. If you multiply it by 2 and you move, this is what we did yesterday, moved everything on the left, you see that the connection defined by B and A on S is ASD. So this means that you have an associated elliptic complex which is associated to this induced connection. So let me write it like this, A0 of S. And here is the operator associated to B square tensor A dual. Here is A1S. And here again is D plus associated to the same connection, B squared tensor A dual, A top plus S. And this is a C-linear complex because S is complex. It's a complex line bundle. This is very important. So this is C-linear elliptic complex. In particular, the harmonic spaces H1B squared tensor each I, let me like this, A dual are naturally C vector spaces, finitely dimensional, of course, vector spaces. And we can compute the index. So H1, so let me like this, dim over C, so accurately, of H1 of this B squared tensor A dual minus dim of H2 B squared tensor A dual minus dim of H0 B A dual can be computed easily, and the result is the following, is minus the dimension everything over C is minus C1S squared plus B1 minus B top plus minus 1. So this is the result, the dimension over C. It's easy to see that this is 0 because a section, I mean an element in this H0 will be a parallel section of S. And this cannot exist because we suppose this would, if you have a section in S, please note that can be identified with Hom L and L orthogonal. Yeah, this S has been in fact obtained like this. So you cannot have non-trivial parallel morphisms from L to L orthogonal because this would make them isomorphic, and they are not. We suppose they are not isomorphic. So this is 0. Now, the point is that now I give you the result. What happens if you let now B vary, or maybe more accurately said, its class, its gauge class, in the torus, each gauge class will be in our torus. So you'll obtain, and you look at H1, yeah, you obtain a linear fibration, of C linear fibration. The dimension of H1 might jump in the general case. Okay, but suppose that it's not the case. This is sufficient for our purposes. So in this way, we get, in fact, a complex vector bundle over the torus. Yeah, the complex vector bundle constructed with these H1s as fibers. And you can projectivize this vector bundle over the torus, and to get a projective bundle. And now, using this projective bundle, we can describe easily a neighborhood of the torus in the moduli space. So let me give you the result as a technical proposition. Suppose B plus of M is 0. This is very important because this will vanish the two cohomology of the sum direct complex, of the whole elliptic complex CA, coming from the first summand. Automatically. B plus is precisely the dimension of H2 plus, and H2 plus here, cocker of D plus here is precisely H2, our old friend, H2 plus G. So this one. So this means that if B plus is 0, this will vanish. Yeah, so at least we have no obstruction coming from the first part of the complex. Suppose also that H2, now let me here denote all these spaces by H1. No, maybe it's not pedagogical to denote it by H1b because one might think of something different. Okay, so suppose also that H2 is 0 for every B in our torus M A of L. So this is a torus. Yeah. Now, what happens if this happens? Then you also killed the obstruction, the H2 coming from the second complex. You see, you have, I suggest you to have in mind the theorem about Kuranishi local models, which has been explained in detail thanks to the question asked at the end of the first lecture. And you know very well that this H2 complicates the description of the local model. Yeah, because the equation appearing in the local model, Kuranishi local model, takes values in an H2. Yeah, so if you know that H2 vanishes, there is no complications. Yeah, you have no complications of the local models coming from this equation, from the equation K, kappa, anyway. So suppose that this holds, and then for every B in the space of solutions of the equation star, here, okay, let me put it here like this. Yeah, I need an exponent here to point out that it's a space of solutions. Yeah, so it's not just a configuration space, but a space of solutions. So this is the definition. BASD for every. Consider the following objects. P of H1 of this B squared tensor A and its cone. And it's in the topological sense. C, let's say B, by definition, is a cone over this base. Cone in the topological sense. And here you projectivize as complex space. What does it mean cone? Cone. This is cone in the topological sense. So you take the cylinder, the product with 0, 1, and we collapse let's say, the product with 0. Yeah, you know what? Wait, understand? So if you have a base B, So this is a base, any space. You take first the cylinder, you multiply it with 0, 1, and then you collapse to a point. So cone over B, by definition, means 0, 1 times B, factorized by the equivalence relation, which collapses to a point, this topological cone over a space. Okay, now, what is the result? The result is the following. Our space of reductions RL has a compact neighborhood in the whole space MASDAL, whose fiber, oh, this is very good. Which is a fibration over the torus, whose fiber above a point is precisely the cone. Let's say, which is a locally trivial bundle over this torus, over the torus RL, whose fiber over an orbit B in MAL is our cone P of H1 of B I said locally trivial. What happens? Why locally trivial? Because you see, fortunately, the hypothesis that our assumptions imply that the linear fibrations given by the H1 is in fact a bundle. There are no jumps. There are no jumps. Why? The index formula in our, you see, we have assumed that H2 vanishes always, and H0 we know that it vanishes. I explained why. So this means that for H1, the dimension of H1 will coincide with the index. So it's constant. So using this, there are no jumps in the dimension. One can prove that with these H1s, one can form a vector bundle. We projectivize it. For every point in the torus, you construct the cone, and you take the union, and you obtain a neighborhood of the torus of reductions in the moduli space. Very interesting case, so no remarks. Suppose that this index, so we have there, so this is precisely minus C1 S squared plus B1 of M minus B plus. So here B plus of M under our assumption is 0. Yes, minus 1. This is B0, of course. Suppose that this is 2. Yeah, suppose that this is 2. Then we have a strange phenomenon which happens only in this case. Namely, the moduli space will be smooth at the points of the reductions, which is very, very special. Why it is smooth? Then, let me write it, then M, our moduli space, is smooth. Is a smooth manifold. At the points of RL. Why? Because in this case, if you projectivize C2, a two-dimensional vector space, you obtain P1. But P1 is the sphere S2. And the cone over the sphere S2 is the disk D3, yeah? Which is smooth, has a natural structure of smooth manifold. So what you get as a neighborhood, you get a tubular neighborhood of the torus, which is just a D3 bundle over the torus. So this is a smooth, has natural structure of smooth manifold. Okay, so this property will be used in my last lecture about from to tomorrow. I will use the structure of the moduli space around the Tauraev reductions, which will be circles. You'll see immediately why. Okay, so now let me come to compactness. This is a very important Donaldson theory. So let me write it like this. We have now difficult problem in Donaldson theory compared to Seiberg-Witten theory. So if you ask a gauge theorist why Seiberg-Witten is considered to be easier, simpler, more effective, defined to the compactification. For instance, cohomology classes and so on. So this is the kind of problem of problems which are on Seiberg-Witten. Yeah. So what is the result? Let's say theorem. So the moduli space itself is not compact, but can be compactified in a controlled way by adding moduli spaces of the same type associated to bundles with lower Chern classes, multiplied with the symmetric powers. So what you do, so for every natural, let's say K, so this is a French notation, and star, I think in the British tradition, n means already n star. I think so. Anyway, so this means strictly positive natural number. Let A, let's say, write me like this, C minus K. So first of all, let C denote, by definition, the second Chern class of E. Yeah, this is my notation. This is an element of H4 of M and Z, which has, of course, isomorphic, identical, canonically, because we fixed our orientation to that. So C to bond on M with C2 of C minus K is C minus K, but the same determinant. So I even write the same, equal. Yeah, you can do that. Yes. A abelian connection A. Then there exists metrizable compact topology. On the union, I will not introduce any notation for this union, and I will explain why immediately. So what you do, first you take your moduli space you started with, and then you make direct sum over K in n star of M ASD. This has sense because you identify the determinant line bundles E say minus K times the K symmetric power of the base manifold M. Now, this is scaring because you can get the impression that this union is infinite. It's not. Thanks to the topological constraint to the existence of an instanton, of a projective instanton, I explained to you in the first lecture. So the condition is, so delta of E say minus K must remain positive, which means that you must have something of type 4C minus K minus C1 squared of E is positive. Yeah, so this gives you a bound on K in the good sense. Yeah, so you see that it means that 4K is bounded by delta of E. 4K so is bounded by delta of E. Yeah, so you can formally omit this, but knowing that as soon as this inequality is violated, then everything will be empty. So the phenomenon which explains this result is again bubbling. Bubbling in the sense of instanton. So what bubbles, in fact, is the curvature. So if you try to check compactness in the initial moduli space, in this one, you take sequences and you look what happens with the curvature, or more precisely to the curvature distribution. You measure in every point the curvature. You take in every point its norm, and you square this norm pointwise, and you get a function, a positive function on the manifold. And what happens is you can prove first that you can choose a subsequence such that the sequence, let's say, of measures converge in the distribution sense. And the convergence, the limit is controlled. So you can only have a Dirac type divergence in finitely many points. And also the masses, the total masses of such a Dirac summand which will appear can be controlled. So this, and you have for every point where a Dirac distribution appears, you have a well-defined multiplicity. And taking these multiplicities into account, you get an element in the symmetric product. And on the complement of these singular points where Dirac distributions appear, you have convergence modulo gauge to an instanton, but in another bundle, in a bundle with a lower Chern class, second Chern class. And this is the idea. I explained to you the proof, in fact, how one obtains this. Such that the initial stratum, MASDA of E is open. Yeah. However, you see, I was tempted to write M bar, MISD bar, and I often do this. But this shouldn't be done with, let's say, with young people, because this might give the wrong impression that you have a closure there in the topological sense. You might have the impression that what you get here, so that this compactification is the closure in a topological sense of this. This is not true. So this means that this stratum, this first stratum, I said it's open, it's not dense in general, like in Gromov-Witten. Yeah? You might have strange phenomena. For instance, you look at, this is called the lower strata, and they might come with components, with oversized components of this type. So this might be the generic. This might happen, as in Gromov-Witten. Yeah, so this is why, I mean, here people argue. Donaldson, in fact, defined his compactification as the closure of the generic stratum in this compact union. Here, there are two interesting things which can be said, remarks. First of all, what is the lowest stratum? Of course, the lowest stratum can occur only if delta of E is if multiple of 4. Otherwise, you don't have it. So the stratum which gives you here equality. So in other words, what can be said about the moduli space associated to a bundle E which satisfies the topological constraint with equality? Yeah, this is now the question. What can be said? So suppose that delta of E0. So you have topological constraint satisfied with equality. Okay. Then in this case, if you have a solution FASDA of E, then you remember the topological constraint has been obtained how? Proving that the L2 norm squared of the trace-free part of the curvature can be identified with delta of E. So if delta of E vanishes, then the whole curvature will vanish. The trace-free part, F is 0, will be 0, which means that, so this is equivalent. If the condition, this means that A is projectively flat. Projectively flat. What does this mean? What it means is that if you look at the holonomy associated to such a connection, then the holonomy is scalar. So you get the holonomy, you look at the holonomy around a closed loop. Yeah, the holonomy, such an holonomy can be interpreted as an automorphism, as a unitary automorphism of your fiber. Yeah, so the point is that a connection is projectively flat if the holonomy is always scalar. It's a scalar multiple of identity. Yeah, so this scalar, of course, must be in S1. And this will be determined by the holonomy of the fixed connection A on the determinant line bundle, of course. This must be determined by that one. So this means, what means projectively flat? So this means that ignoring scalar multiplications is flat. The contribution of the holonomy becomes trivial. All the holonomy become trivial as projectively flat. So and in this case, one can identify our moduli space, let's say, is closed and open. Closed and open in a moduli space, very interesting, in a moduli space of projectively flat connections. What they are defined, probably many people know about the correspondence between flat connections and representations of the fundamental group of a moduli space of representations from P1 of M, let's say at a point x0, in PU2 or SO3, modulo SU2 conjugation. Modulo SU2 conjugation. Yeah? So the point is that SU2 acts naturally by conjugation on PU2. Yeah? A PU2 is, so PU2 can be regarded as SU2 factorized by plus minus identity. And if you pick here, let's say an element here in this quotient, you can conjugate it with an element in SU2, yeah? And in this way you get a well-defined SU2 conjugation in the space of representations with values in PU2. Yeah, so a bit finer than the natural conjugation defined by PU2. Anyway, so this means, you see, this is very interesting that this moduli space is G-independent. It's G-independent. Yeah, so does not depend, it's a moduli space of representations. So does not depend on G. So this stratum is very, very important and meantime difficult. It's difficult. Why it's difficult? Because cannot be changed if it's bad. For instance, if it's oversized, you cannot repair your situation. You cannot change anything by changing the metric. You see? So it's already comes in the it always comes in the compactification. You cannot avoid that. If, of course, if the delta of the initial bundle is divisible by 4. So, in particular, the expected dimension can never be realized by changing the metric. Remarks, this is 1. And 2. If delta E is less than 3, then the moduli space is already compact. This is extremely powerful. Extremely powerful. Yeah, because as soon as you take here a K, which is strictly positive, you see that delta of this bundle is already negative. Or if you want, if delta is bounded by 3, then you cannot realize this with a strictly positive K. Yeah, this is the same thing, if you want. So the first stratum, which you should add in order to compactify, is already empty. So there is nothing to be added. Yeah, however, there is no other way to prove this. The only way is to prove in general the result, and then to get this a very special situation. This compactness property plays a huge role in the whole story. So the way in which I applied the Donaldson theory to get information about curves on class 7 surfaces uses compactness essentially. Okay, now maybe there is the right moment, as I promised yesterday, to say several words, not more, about first Donaldson theorem. Yeah? About the first Donaldson theorem. Let me theorem. First Donaldson theorem. Donaldson theorem. So, as I was a student, this theorem appeared and was sensational result. And maybe in 5 minutes, I will explain you now why this result was. First of all, unexpected, surprising, and why it can be considered to be, let's say, opening a new way of obtaining results in differential topology, a new way, a new strategy, which had nothing to do with the topological methods used in the past. This is what I want to point it out. So why it was considered so spectacular and interesting. So the result is the following. Let M be a smooth four manifold. Manifold, which is as usually closed, connected, oriented, with, say, negative definite intersection form. Definite intersection form. Idest with B plus M is 0. Then the intersection form of M is standard over Z. Is standard over Z. Id est, there exists a basis E1, E index B2 of M in H2 MZ over torsion such that EI, so making the products of this, you obtain minus delta ij, such that Qm of EI Ej is minus delta ij. What is the intersection form? So the intersection form is defined by the cup product evaluated on the fundamental cycle. So it's defined like that. Correctly should be defined like this, over torsion. Why? Because in this way you get a free module of dimension B2, rank B2, H2MZ over torsion with values in Z. The condition that the intersection form is definite means the following. You tensorize this with R. You tensorize this with R. This Z module, this free Z module, you can tensorize it with R, and you get a B2 dimensional vector space. The intersection form by Poincaré duality is unimodular, and so in particular is non-degenerate, regarded as a bilinear form on this vector space is non-degenerate. This is what you know. And by the properties, external properties of the cup product is also symmetric. So you have a symmetric bilinear form which is non-degenerate on a vector space. You can look, if you want, at the quadratic, associated quadratic form and the classification of quadratic forms over R, inertia law. Yeah? And then definite means that, in our case, negative definite, the signature is 0B2. Yeah? So you have no negative terms in the Gauss standard form of your quadratic form. Yeah? This is what negative means. And then Donaldson says, okay, then you can find in this Z lattice a basis which makes your form standard. What is interesting is that the theory of bilinear unimodular symmetric forms over a Z lattice is very difficult. It's not at all true for a general unimodular symmetric bilinear form is not at all true in general, that if it is negative definite, it's standard. Yeah, so it can be brought to the standard form over R, but not over Z. And there are plenty, for instance, minus E8, if you want, there are plenty of bilinear unimodular symmetric forms which are there's a negative definite, but they are not standard over Z. Okay, and what is, I cannot give you here details about the proof, but just let me give you the rough idea how the proof of Donaldson started and why I said this opens a new philosophy, a new way of proving differential topological results. So let's say proof of idea. Idea of the proof, excuse me. Idea of the proof. Of the proof, let's say for the initial proof appeared for P1M is 1. Is trivial. P1M is not. This is the original proof of Donaldson, which was so famous, so spectacular. Fortunately for us, Donaldson came back to the problem several years ago with a much more difficult paper proving the same statement in the general with any restriction on P1. And this plays a crucial role in my proof because I don't impose anything on the fundamental group. So I start with Donaldson theorem, I apply it to a class 7 surface. Yeah, and I know that I can deduce that the intersection form is standard over Z. The idea of the proof is the following. Consider an SU2 bundle. So let E be a SU2 bundle. This means that D is trivial, not only trivializable, but very trivial, and A is the trivial connection on this trivial line bundle. The SU2 bundle over M with C2 of E is 1. Of C2 of E is 1. Then you see that in this case, so C2. So in this case, delta of E will be 4. And the moduli space can be compactified. So you have a compactification, MASD. Let A here, I can skip it because it's the trivial connection. MASD of E. And what I have to add is one stratum, but which I know. Why I know? Because the only stratum I have to add is precisely the stratum which corresponds to flat connections. And because P1 is 0, you have only one representation of the fundamental group, which is the trivial one. So this means that here you have the trivial representation of the fundamental group, because the fundamental group was trivial, I suppose that, times M. And this is already compact. The expected dimension is 5. Dimension 5. And Donaldson studied what we did, reductions. The reductions. And he obtained what we did for every topological splitting of E, a torus, but because B1 is 0, his torus was a point. Yeah, but he also used our local description of the moduli space around the reduction. In fact, the opposite was true. I generalized his statement about in his situation to the case B1 arbitrary. What is the moduli space? The moduli space has this shape. This is the lower stratum. This is M. Yeah, so this is M, but obtained how? As a product of the trivial representation times S1M. This is the lower strata you have to add to compactify. And here you have, for every topological splitting, let's say for every topological splitting, E is L. And here, in order to have determinant trivial, the other one must be the dual of L, yeah? Because the product D is trivial. So L orthogonal is L dual. Topological splitting of E. Let's say this topological splitting, let's see, denote it like this, sigma. This is a pair L dual, unordered pair. Yeah? One gets a reduction P sigma, so this isolated reduction in the moduli space. Why isolated? Because the torus reduces to a point, as I said, in M, ASD of E. And we know how the neighborhoods look like. They are cones over a projective space. And this projective space is CP2 in this case. So P sigma has a neighborhood, let's say isomorphic to cone over P2, and if you look correctly at the orientation, is P2 conjugated, if you take the orientations into account. And Donaldson proves here a color theorem. So the compactification, you have here the compactification. Let me, in this case, write it M bar, because this is really a closure in this case, this particular case. So M bar is, let's say, a 5 manifold with boundary M, and is oriented, is not oriented with boundary M. If very interesting, the points of M appear as bubblings in the moduli space. And now, Donaldson did two things, both of L easy. As soon, this is the point, as soon as you have this picture, the proof becomes easy. As soon as you understood the moduli space, the proof is easy. What he did, he counted the number of sigmas. This is easy to do, very easy to do, because what you have to look is that the possible let's say topological types of L. So at their Chen classes. And the number of splittings using this idea, let's say the number of reductions is the number of solutions of the equation x squared is minus 1. X, of course, will be the Chen class of L, where x is in H2 of M and Z. Yeah. Why? Because if you split A, the Chen classes will be x and minus x, minus x. And the second Chen class will be minus x squared. So the Chen class, the second Chen class is 1 if and only if minus x squared is minus 1. By x squared, I mean, of course, qm of x. Now, this should be formally written like this. X in H2 of mz with x squared is minus 1. And as I said, order is not essential, factorized by the action of plus minus 1. Yeah, it's a cardinality. And what Donaldson also proved, that he removed these standard neighborhoods of the singularities removing these neighborhoods. So neighborhood has a neighborhood isomorphic to, voila, denoted this by n p sigma. Yeah? He removed and he obtained a manifold with two boundaries, let's say. One is M and the other is a disjoint union of projective spaces. Yeah? So M bar minus of the interior of n p sigma, like this. This is formally perfect. This is a cobordism between M and so let me denote by K this number, this cardinality, K and P2 squared. And he just wrote that the signature is the same. Yeah? The signature is the same. So what he obtains, the signature of M is minus B2 of M, because the negative form is negative definite. This is the so invariance, signature invariant. Hirzebruch theorem, invariance. The signature of a four manifold is an invariant of the cobordism class. So minus B2 of M is minus K. And one can very easily prove then, so this means that you have sufficiently many solutions to this equation, and it's easy to see. So this means that K is the rank of the lattice. And this very easily, with a very easy algebraic argument, proves that, in fact, the intersection form is then trivial. So if you have sufficiently many solutions to this equation, then you can prove that, in fact, your intersection form, your bilinear form, is trivial. So it follows that QM is standard. So what I mean is new. Because you start the proof with an object which apparently has nothing to do with the problem you study. You want to get information about the intersection form of the manifold. So this means about two cycles, how the two cycles embedded in the manifold intersect. This is what you want to study. This is your goal. And you don't start the proof with any two cycle at all. What you start your proof with a moduli space of instantons. This is what I said was something radically new compared to what has been done in geometry and in differential topology up to that moment. Okay, so now, what is very important now, so we have time to talk about 25 minutes, I suppose, about the Kobayashi-Hitschin correspondence. The Kobayashi-Hitschin correspondence so since we do have time, let me explain you first what is this correspondence. What is this? What is this good for? What has been used in the past? For which purpose? For which purpose has been introduced first in mathematics? What was the goal, the motivation? And in which way I'm going to use it? Yes. So this is, we have time to explain this in detail, and this I hope will make the story, let's say, more interesting for you anyway. We have time to say something about history. So what it's about? So the idea is it relates the concept projectively ASD introduced by us, projectively ASD connection. So a point in our solution space A, ASD of A and E, anyway, relates to stable or polystable holomorphic bundle. Holomorphic 2 bundle. Supposing, of course, that M, G is a Hermitian surface. Is a Hermitian surface. We'll need a bit more Gauduchon, but in fact, everything can be done in the Hermitian situation. So if the base is complex, the idea is if the base is complex, then our difficult moduli space of instantons have a complex geometric holomorphic description in terms of holomorphic bundles, stable holomorphic bundles. This is let's say, the rough idea, which is in fact remarkable because it's a bridge between two worlds. Don't forget that the ASD connections, please, have to remember that an ASD connection, the definition was very easy to write down, thanks to the modern differential geometric formalism. Yeah, the curvature written in the modern differential geometric formalism is easy to define, but you know that it hides a very complicated object. Yeah, it's a tensor, and this tensor contains the first derivatives of the components of the connection, which means that a projective ASD connection is in fact a solution to a very complicated nonlinear PDE system on the manifold. What you have on the left is global analysis on compact manifolds and difficult complex analysis. So you have difficult equations, and not only that we have to study the space of solutions, but to factorize by infinity dimensional gauge group. So it's difficult. So, but anyway, on the left we have global analysis. On the right we have complex geometry. So, and the idea of Donaldson was, in fact, he applied this correspondence in order to compute his moduli spaces. And this is what he succeeded. He computed. So before proving that theorem I mentioned there, he concentrated, he succeeded to compute moduli spaces of instantons on complex surfaces, on Dolgachev surface, for instance, and to distinguish using his invariants, Donaldson invariants. I don't have time to introduce them. So he succeeded to prove that certain complex surfaces are homeomorphic but not diffeomorphic. Anyway, so this was, the point is that the Kobayashi-Hitschin correspondence has been first used by Donaldson as a tool to compute moduli spaces of instantons. I will use it in the opposite sense. I will use it in the opposite sense. So for me, let's say the unknown will be the right-hand side of the correspondence. So I'll use information coming from gauge theory, for instance, compactness, to get information about moduli space of bundles. Anyway, so now come to the definitions. Let G X be a complex surface. In the sense of my first talk, so it's compact, connected, two-dimensional manifold. And G, a Gauduchon metric on X. This means id est, G is Hermitian with d bar omega g 0. Omega g is still called the Keller form of G, even if it's not closed. It's a real two-form of type 1, associated to G, and the complex structure regarded as an almost complex structure, as you've seen in the lectures about symplectic geometry. So having the G Hermitian metric with respect to J, the almost complex structure, then you can use them to construct with the same formula a two-form which will be non-degenerated, and it is called omega G because the complex structure is fixed. But you don't have, of course, in general, any reason to expect this form to be closed, and it is not. In general. Yeah. This is why Gauduchon came with this idea to replace Kellerianity with his Gauduchon condition. And this Gauduchon condition, maybe I would say that in dimension n, the correct formula here is with omega G power n minus 1. Yeah, this is important because people use, seeing this might be tempted to generalize in the wrong way. So for n-dimensional manifolds, one imposes or requires dd bar omega G n minus 1 is 0. And the point is that there is no obstruction to the existence of Gauduchon metrics, fortunately. So we can find Gauduchon metrics on every compact complex manifold. So there's no obstruction. Okay, then what you can do is to associate to this metric a concept of degree, the degree of a holomorphic line bundle, and stability. And this can be done in the following way. If L is a holomorphic line bundle on X, then and H a Hermitian metric on L, then one can associate to these two objects what is called the Chern connection of the pair. The Chern connection of the pair. This is very important. I'm sure that here in Grenoble, this is a very popular concept. This is the unique Hermitian, H-Hermitian connection, whose 0,1 part is a Dolbeau operator associated with the holomorphic structure of L. And it determines the connection in a unique way. And the point is that then one have a Chern form is by definition I over 2pi, the curvature of this Chern connection. This is not only a Chern class. It's not a cohomology class. It's a form which depends on H. So one can prove that it's independent of H up to a dd bar exact form. So up to the image of this dd bar operator. And now one defines the degree with respect to G of L is by definition, we integrate this omega G. This is well defined. Well defined. By double integration, parts integration, one sees that, okay, if one changes the metric H, the Chern form will probably change, might change with the dd bar exact form, but applying Stokes' theorem twice, you see that after integration, the change of the integral vanishes because omega G is dd bar closed. Yeah, so this is what happens here. It's well defined, and one obtains in this way a degree map, dig G, defined over peak X with values in R, which is a morphism of Lie groups. But in general, it's not a topological invariant, so careful. So this means that cannot be expressed in terms of the chain class, topological chain class of L. So, example. If X is a class 7 surface, then peak naught of X. You know, peak naught of X is the group of the holomorphic, so L holomorphic line bundle on X with C1 L holomorphic line bundle with C1 of L is 0. Pical. Then for a class 7 surface, this is the definition. And then is isomorphic to C star. You see, non-compact. It's not a torus. It's the non-Kählerianity phenomenon. You don't have the components of the Picard group are not compact. It's still an abelian Lie group, yeah, but it's not compact. And not only that, but you have an essentially canonical identification. The point is that any element in peak naught has a unique holomorphic flat connection. So it's defined by the representation of the fundamental group. And since H1 is Z plus torsion, no? Anyway. So you see that essentially given such a representation means to give the image of the generator of H1 modulo torsion, of homology 1 modulo torsion. So an element in C star. Automorphy factor. So you have this, and you can prove that deg G of L zeta. So here, if you take a zeta here, you have an L zeta holomorphic line bundle here. And you can prove that this is the constant, which depends of the metric, yeah, multiplied by the logarithms of the absolute value of Z. Very interesting. So you see that the level sets of the degree map are circles in C star. And CG is always positive if you choose this identification correctly. So it has always the same sign for every Gauduchon metric, every G Gauduchon. So for appropriate identification. For appropriate identifications. Now, definition. Let E, now, maybe the right moment to point this out. For bundles, the calligraphic letters will always be reserved for holomorphic bundles, for bundles endowed with holomorphic structures. So remember the question George asked, I think yesterday, about our L, which has been used yesterday. He thought at a holomorphic line bundle, because very often in complex geometry, L denotes holomorphic line bundle. In my notations, including in this lecture, also in my paper, I use this convention. I reserve Roman letters for differentiable bundles, vector bundles, and calligraphic letters for holomorphic. And then no confusion will be possible. We see immediately in which category we are. Let so be, let's say, a rank 2. So I just explained you the theory in general. A rank 2 holomorphic vector bundle. on X. So E is called G stable if the following, if for every sheaf monomorphism zero L E, one has dig G of L is strictly smaller than what is called the slope of E. Dig G of E. By definition, the degree of E is, of course, the degree of its determinant. So as soon as we have the degree on peak, on line bundles, we can extend it even on any coherent sheaf. Because the determinant, very important. The determinant line bundle is well defined on the whole, let's say, category of coherent sheaf, of analytic coherent sheaf on X. We can define, and even for the most singular coherent sheaf you can imagine, the determinant is still a line bundle. Anyway, but we don't need this. This is a very important. This is called the slope of E. So the degree divided by the rank is called G stable. And in the same definition, so this is the first part of the definition. Let me start it like this. E is called G polystable if it is either G stable or it splits as E is L tensor M. Now I don't have to avoid confusion with notation of the base, with the same degree. With degree GL is degree GM. Or if you want, okay, if this is true, then both of them will coincide with the slope of E, because the degree is additive. So if you have this, the degree will be the sum. So this is one can formulate this in this alternative way. One can say that E has a direct summand which has as degree precisely the slope of E. So you see, if you have, let's say, a way to classify holomorphic bundles of rank 2, these objects, let's say, are understandable. If you know these bundles and you also can control all their subsheaves, by here I mean careful. I mean a sheaf monomorphism, and this is serious, man, serious. What I mean here, you see, one has to distinguish between bundle embedding and sheaf monomorphism. Yeah, the point is, imagine, for instance, that you have a non-zero section in a vector bundle. Yeah, it might have zeros. It might vanish, yeah, in isolated points or even on divisors. However, such a section induces a sheaf monomorphism from O, from the structure sheaf to E. Yeah, because at level of germs of sections, the map will be injective, but not fiber-wise. So won't be a bundle embedding or monomorphism, but will be a sheaf monomorphism. Here I mean sheaf monomorphism. Anyway, so now notation. Let D be fixed holomorphic structure on D, which was that E is differentiable. EH is Hermitian, because it's a Roman letter. Hermitian 2 bundle on X. I fixed holomorphic structure on the determinant precisely as in gauge theory I fixed a connection on D. Now I change everything. Everything is now complex geometric, is holomorphic. I fix holomorphic structure on this differentiable line bundle. And I denote by M stable D E the moduli, let's say space, and I explain for instance, of holomorphic structures of on, I think it's the accurate in English, on E, inducing precisely the fixed one on that E. So you see, we vary. You look at the possible holomorphic structures on E, but we fix the induced element in peak. You see, one can regard it in the following way. Let's say the classification of holomorphic bundles in complex geometry is understood. We have this peak. We know its structure. We know how it is defined. This peak, which classifies holomorphic bundles, we are no longer interested. We are no longer interested in varying line bundles because we know what is the moduli space. Then why to vary the determinant line bundle? We don't, because we know in which space it varies. We keep it fixed, and we vary only the non-abelian part of our consider. So the moduli space has a natural complex space structure. Complex space structure. Might be singular, but it's finite dimensional, and it's open in a more of a larger, I don't have time to speak about it, in the moduli space of simple structures on E. These are the structures having no other endomorphisms but only the constants, the homotheties. And this is also a complex space, but it's in general non-Hausdorff. Of a natural, so has a natural complex space structure, which is Hausdorff. And this is open in this one, which in general not Hausdorff. Not Hausdorff. Now let me state the Kobayashi-Hitschin correspondence, because we did everything it's necessary to do it, to write it down. Theorem. This is called Kobayashi-Hitschin. However, in this non-Kählerian framework, I mean, who are the real authors? It's difficult to say. In the non-Kählerian framework has been first stated by Yao and two collaborators, but I think a complete proof can be only found in my book with Martin Lücke, also quoted. States the following. You take a connection on the Hermitian bundle A, and you look at the covariant derivative I was speaking about many times in this lecture up till now, and you look at the 0, 1 part. The 0 part is defined on A0E of A01E. So this is the 0, 1 component of dA. Is not a new object. But using the complex structure on the manifold, the covariant derivative splits because the 1 forms, the space of 1 forms split in 1, 0 and 0, 1. This so defines a bijection between MASDAE, here Kobayashi-Hitschin, in the moduli set, polystable here, structures of E. I didn't introduced formally because it has not the structure of anything. Even topology is not defined. This is the moduli set of polystable structures. Moduli set of polystable structures on E, inducing, of course, determinant, the fixed determinant line bundle. Induces objection, which restricts to a real analytic isomorphism. Isomorphism between the irreducible part, MSDE star, and the stable part, which has even a complex space structure. This is a statement. So this means you can regard it in two ways, as I said, as a tool to compute instantons moduli spaces with complex geometry. You classify your two bundles with a given topological invariance and the fixed determinant. This calligraphic is. And as a set, at least, if you also include the polystable ones, which correspond to the reductions, of course, then you get the whole moduli space of instantons. The difficulty is that, let's say, at the split polystable points, on the right-hand side, you don't have any reasonable structure, even on topology. But on this bijection, if you restrict it to the open part, to the open part built by the irreducible instantons, then this can be identified with a classical complex geometric moduli space of stable bundles. So this is the statement. What we will do, but I will explain tomorrow in my last lecture, we will use this bijection to put a topology here. And this is very important. Topology on this complex geometric moduli set is by definition the unique topology which makes this bijection homeomorphism. There is no other way to understand, to put in a with complex geometric methods a topology on the right-hand side. Okay, so I think I will stop here. What will happen tomorrow? We'll apply all this to class 7 surfaces to a very special E, and with this moduli space, we will get, using the geometry of this moduli space on a class 7 surface, we'll prove existence of curves. And the curves will appear by writing to the same rank 2 bundle, stable bundle, writing as extensions of line bundles in two different ways. And chasing diagrams will get morphisms between line bundles, which are non-trivial, and the vanishing locus of such a morphism will be a curve. Thank you very much. What I said, what I said, if you, So what is formally proved in my book with Martin Lübke is that the sign of the constant is independent of the metric. Okay, and then my statement had a bracket, which I wrote on the blackboard. I said the constant is always positive for appropriate identifications. What I mean, if you identify in a convenient way, pick 0 with C star. If you identify because you have two identifications, you can compose with the inversion of C star, of course. But if you choose this identification in a convenient way, then the constant will be positive.
Yes, but in applications, negative choice is more convenient, no?
Okay, but the point is that you can make a choice. What is formally proof in our book is that, as soon as you fix the identification, the sign is independent of G. And then, of course, if you prefer negative constants, you just change the conventions. But, okay.
So,
yes?
So we know how to compactify the this moduli space. So the correspondence for the compactification of center moduli space. So it means that how can we compactify the set moduli space?
So this is a very good question, because one of the main results, which will be proved tomorrow, will be that for the special choice I will make, the moduli space will be already compact. Yes? But the proof uses the Uhlenbeck compactification. Yes? First of all, for smaller B2 will be in this favorable case where delta is bounded by 3, and then will be automatical, for topological reasons. So this will be compact. And then, because the topology here has been defined such that this is isomorphism, this will be compact also. And for general B2, I will prove compactness with complex geometric methods, but again, having in mind the Uhlenbeck compactification. So I'll prove that the lower strata are empty. Maybe I don't know if I understood correctly your question. Maybe your question is if you can, let's say, compactify in a complex geometric way the right-hand side such that the Kobayashi-Hitschin correspondence extends to the compactifications. The answer is it is known, it is done for the projective case by Jun Lee many years ago, that this is the case. But nothing has been done in the non-Kählerian framework, even Kähler, non-algebraic. This is not studied. So it's a complex geometric version of the Uhlenbeck compactification. So you have to work with torsion-free sheaves, with singularities, and so on. And this has not been done in the non-Kähler. But fortunately, we can avoid all these complications about compactifications tomorrow, because my choice of E will imply automatically compactness of the main stratum. So we don't have to add strata. Yeah, it's okay?